I want you to go ahead and imagine an ideal vacuum, a vacuum with absolutely no matter inside of it, and I want to ask you, what is inside the vacuum? Intuitively, there is nothing inside of but empty space, but what is actually really profound is that empty space is not actually entirely empty. In fact, quantum field theory, a major part of quantum mechanics, the science of the really small, suggests that empty space is actually teeming with a sea of virtual particles coming into reality and popping out of reality like the static on a television screen. And these particles help explain many phenomena, even describing how black holes, the most powerful sources of gravity, can evaporate over time, and I believe it may explain gravity itself. But what are virtual particles, and where do they come from? Imagine empty space as a series of points. If you add energy by introducing particles or photons to one of the points, it will oscillate with that amount of energy, back and forth in a harmonic motion, affecting points of space around it. The Heisenberg uncertainty principle states that knowledge of two related variables, such as momentum and position, is limited. A version of the uncertainty principle relates energy and time, where the information for both is limited. If we combine our definition of space in a vacuum and the uncertainty principle, then we can conclude that the points in space will follow the uncertainty principle and never have energy equal to zero. In this picture of a vacuum, space is a sea of swirling points in space that constantly changes, causing what are called quantum vacuum fluctuations, where the energies of all the points in space constantly switch between different energy levels by oscillating back and forth. These fluctuations in energy in the vacuum become vacuum energy. Yeah, this is quite weird how energy can exist in empty space and not in actual particles. But what's even more interesting is that this concept can be proved mathematically. Let's look at what's called a quantum harmonic oscillator. Don't be discouraged by the name. It's just a graph that shows possible energy levels of the vacuum energy described earlier. Every escalating n adds an extremely small amount of energy to the vacuum called a quantum. What is really interesting about this diagram is what is called the 0-point energy, or the energy of the ground state, the lowest possible energy allowed in a quantum system. From this point up on the graph exist real particles, like electrons. No real particles can exist below the 0 point. The energy lower than the 0-point energy is so low that it cannot exist in real particles. Everything in this area below the 0 point is actually just disturbance in the vacuum energy that we call virtual particles. It is important to note that virtual particles are not actually real particles, but rather just disturbances in the vacuum energy that can push the vacuum energy described earlier over the 0-point energy. Virtual particles must arise in pairs. With a matter-antimatter pair, vacuum energy can manifest itself in tiny particles of matter and antimatter that can arise spontaneously and annihilate themselves almost immediately after they are created. A virtual photon pair can also arise spontaneously and annihilate, despite having no rest mass. An important thing to note is that the more energy contained in the virtual particles, the less time they have to exist. As previously stated in the Heisenberg uncertainty principle, the knowledge we have of the energy and the time of a quantum system is limited. If the time is significantly less than h bar over 2, the value of the lower limit of our possible knowledge of both variables, then the energy must be very great in order to bring the value high enough to obey the equation. Conversely, if the energy is significantly less than h bar over 2, then the time the virtual particle exists must be very great. Another important thing about virtual particles is that they can take any energy and even have attractive and repulsive forces associated with them. But wait, if virtual particles aren't real, then how do we know they exist? There are many ways that virtual particles affect real matter. The experiment that helped postulate the appearance of virtual particles was the Casimir effect experiment. If you take two uncharged metal plates and put them around a micron apart and put them in a vacuum, then they will close together. Why? For any photon to appear, it must complete at least half a phase within the given distance. A small amount of space exists between the plates, limiting the wavelength. Virtual photons that are created between the plates will therefore have a limited range of energy. Wavelengths that are too long cannot appear between the plates. However, outside the plates, any energy a virtual photon can appear. As a result, The pressure from the virtual photons on the outside of the plates is greater than the pressure on the inside of the plates, and the plates are pushed together. Virtual particles are also fundamental to our understanding of black holes. On every black hole, there exists an event horizon, which is the invisible border between the inside of the hole, where gravity is so strong that even light is not able to escape it, and the outside, where light is just fast enough to escape the black hole's gravity. Stephen Hawking postulated what is now known as Hawking radiation, which tells us the mechanism of how a black hole can actually evaporate. On the surface of the black hole, there exist virtual particles everywhere in pairs. Sometimes, when a virtual particle pair appears, one of the virtual particles crosses the event horizon, and its pair becomes a real particle because it cannot annihilate itself with its pair. Where does the energy it took to convert the virtual particle into a real particle come from? The black hole. At a very slow rate, as energy is taken away from the black hole loses mass and can potentially evaporate.